going, right? So we're going to do a practice problem. We're going to start off with this one. So we're going to look at the, basically we're going to draw the Lewis structure for CO2 and carbonate. And then we're trying to account for the fact that the carbon-oxygen bond, why is it longer for carbonate than for CO2? So I'm going to give you guys until probably about 1:05 to kind of start with this one. So let's go ahead and try to do our Lewis structures, and then we're going to talk about this carbonate one. If you finish with that one early, then you can move on to that CF4 or SF4 problem.
Hello.
There we go. So we got a warm-up problem that we're doing. So we're kind of working on this first part of 1999's multiple or free response. So we're looking at part A on this one. So got about another minute or two, and then we're gonna be going through it. All right, so we're going to start with the Lewis structures for CO2 and carbonate, right? Now, what's the first step of our Lewis structures? What do we need to find?
The valence electrons.
Number of valence electrons. So how many valence electrons does carbon dioxide have?
Is it 4? Oh, dang it.
Not 4, right? Carbon is 4. Each oxygen is 6. So you're right. It is a total of 16 valence electrons. So who goes in the middle, carbon or oxygen?
Carbon.
And why do we know it's carbon?
Because it has the most electronegativity.
The most or the least?
Or the least, sorry.
Right? So it's the one we're looking for the one that's not as attractive to the electrons, because the central atom normally ends up sharing the most electrons. Right? So that's why the least electronegative, or really the one in the group farthest to the left, and then the least electronegative, kind of gets that middle spot. So then we have our oxygen, and we have our oxygen here. So that's used up 4 of those electrons. So we got 12 more. And so we can start to fill in from the outside. So we can use all 12. And now each of those oxygens has an octet. We have no more valence electrons. And so is that our Lewis structure for CO2?
No.
No. And why not? What's the problem with it?
No, the carbon doesn't have 8.
Carbon doesn't have 8. Good. So what do we need to do? If we have no more electrons to put in there, but carbon needs more, what can we do?
Borrow from oxygen.
Another one.
All right, we can make a double bond, draw from that oxygen. So we do that once. Is that enough, or do we still need to do more?
More, one from the other side.
Right. Now, why do we do it from the other side instead of just making a triple bond? Why wouldn't we just do a triple bond like this?
It's because the charge, I forgot the name.
You get the assigned charges.
So it's the FOMO charge.
FOMO
right?
charge.
Very good. So a FOMO charge is the number of valence electrons it normally starts with. So for oxygen, that would be 6, minus the number of lone pairs on it, or unbonded electrons, so 2, and half of the bonding electrons. Right? So this one would be 6 minus 2 minus 3. And so it'd be a +1 on this side. And then this one's going to be a -1 on the other side. And so you're right. If we do a triple bond and a single bond, then we would have these FOMO charges, and we don't want that. So good. So we have our double bond there. All right. Who wants to walk me through what they drew for their carbonate ion? What's that Lewis structure look like?
I didn't finish, but I know that it has 18 valence electrons because you need to add the total charge, which is 2.
Now, that seems a little low.
Oh.
Right?
Oh,
Because
3. Oh, sorry, I wrote 2.
because there's 3 oxygens, right? So instead of 18, what should it be?
$22.
22 would be
Plus the-
CO3. We have to add in 2 more.
So it's 24.
So it should be 24. All right. So 24 valence electrons. Who's in the middle?
Carbon.
Carbon. And then am I just throwing double bonds on all of those?
Just in one.
Just one of them. Doesn't matter which one?
Nope.
No.
No. Okay. All right. Now we should bracket the whole thing, and we should put our 2 minus. Good. So our Lewis structures are now finalized. So that was part A for it. And now it's asking us about bond length. So what do you guys know about bond length? What kind of bonds are the longest and what kind of bonds are the shortest?
The longest would be, sorry.
Single is longer, or single bond.
Single bond is longer, not hotter, right? But a single bond is longer than a double.
Double.
And so that also means that a triple bond, how does that compare?
So that's the shortest, right?
The
Double
shortest.
bond is, yep.
And so a double bond's in the middle. Okay. So we're looking at carbon dioxide here, and we're comparing it against carbonate here. And so we're looking at the bond between carbon and oxygen. Okay. So we're looking at any of those bonds between carbon and oxygen. And so it asks us, why is the bond length in carbonate longer than the carbon-oxygen bond in CO2? And so when we look at that, why would our carbonate have a longer bond than our CO2?
Because in CO2 are double bond, both of them.
Okay. And in carbonate, what would it be instead?
I don't know.
What is the question?
So we're trying to compare our carbonate bond length with our carbon dioxide bond length. And so we're trying to figure out why. And so Alex said that that's because the double bonds, right? The carbon oxygen bond in CO2, they're both double bonds. But that's only half of it, right? Them both being double bonds explains that length. But why would CO3s be longer then? So we have to get to the other side as well.
Well, is it because the double bonds are in the middle, so it has one like middle bond, but it then has two longer bonds, the two singles?
Yeah. So I guess my question is, in the actual molecule, are these bonds, is one of them going to be longer than the, or is one of them going to be shorter than the other ones? Or what happens to this molecule when we find it out in nature? Is there more than one way for us to draw this Lewis structure for the carbonate?
Yeah, you can draw it two other ways.
Draw it two other ways. And what do we call that? If we can also draw this like this.
Resonance.
Resonance, very good. So resonance means that our true Lewis structure is somewhere between one of these three. It doesn't look exactly like either one of them, but it's kind of like a mixture of it. In the same way that if you had like a hybrid of a dog, so if you mix two different dog breeds together, you're not going to get a poodle and you're not going to get a golden lab. You're going to get a mix between them, right? And so our structure for carbonate is somewhere between all three of those. Now, does CO2 have a resonance structure? That's like another major resonance structure, or is it only that?
Just that.
It's only that, right? And so you could say that, well, carbon dioxide has a double bond for its carbon oxygen bond, which is shorter than the carbon oxygen bond in carbonate ion, because carbonate has a resonance structure where its carbon oxygen bond sorry, let's shrink this a little bit, is a mixture, or let's say is between a single and double bond length. So we know that that carbonate ion is never going to be as long as a molecule that was all just single bonds between carbon and oxygen, but we also know it's never going to be as short as if it's just double bonds. And so when you answer a question like this, you have to make sure that you talk about both sides. If you only talk about one molecule, you can never explain why the other molecule would be either longer or shorter, right? You can't do a comparison if you only talk about one side. You always have to be able to talk about both, because you have to explain why the other one is different in its comparison. Does that kind of make sense?
Mm-hmm.
I have a question.
Mm-hmm.
Say like I can't think of a molecule right now, but like say the CO2 had like a triple bond and two single bonds, but they each had three resonance. Like, so is the resonance is what accounts for it being longer, or is it like, will we take into factor the triple bond at that point?
So you would take into account the triple bond, right? So resonance doesn't make things longer. So just having resonance doesn't mean that it's longer, right? What's really making it is the bonds that you're mixing together, right? So one way to like mathematically kind of solve this is, instead of just looking at it, is we really want to find this bond order, right? So the higher the bond order, so as bond order increases, then the shorter you become. the lower the bond order, the longer you are. And the thing about bond orders is it's not restricted to just single bonds, double bonds, and triple bonds. You can have any type of bond order, right? So any value there. So how you calculate the bond order is you look at all of the different resonance structures and you see on average, or you basically find the average value that that bond is going to have. So let's say that we're looking at this carbon and this oxygen bond. So the ones that I just highlighted in yellow, right? In the first one, it's a single bond. In the second structure, it is another single bond. And in the third structure, it's a double bond. Now, how many resonance structures were there?
3.
3. So if we add up its values and we divide it by 3, that's going to give us the average bond order it would normally be, right? Because it's a mixture of between a single bond, a double bond, and a single bond, right? So it means that 2/3 of the time, we're saying it's a single bond, 1/3 of the time it's a double bond. And so in reality, it looks much more like a 1.33 bond, right? Is that its electrons get split up, and so we can kind of spread those out between them. Now, when we look at this carbon-oxygen bond over here, you can see that it's a double bond here, and that other carbon-oxygen bond is also a double bond. And so we would be 2 plus 2, and there's 2 different types of those bonds. And so its bond order is just 2, right? So you can use bond order instead of having to do all of this explanation about single bonds and double bonds. You could just say carbon dioxide has a bond, carbon and oxygen bond has a bond order of 2, which is larger than the carbon oxygen bond in carbonate, which has a bond order of 1.33. And so the carbon oxygen bond in carbon dioxide should be longer, right? And that would be it. So if you find your bond order, then you can use that as an explanation, right? So resonance by itself doesn't make things longer or shorter. It just tells you what's mixing together. Does that kind of answer your question, Tiffany?
Yes, thank you.
Yeah. So bond order, in some ways, it's like another thing you have to remember how to do, but it can also make it a lot easier, a lot cleaner when you guys get into those explanations. And so remember, for bond orders, you're really just adding up all of the different options and you're dividing by how many different resonance structures there were. Any other questions about that? So then let's look at our part B here. So I'm going to give you guys a couple minutes so that way you guys can start on part B and then we'll go over that one. So right now it's like 1:20. So how about I give you guys about 3 minutes or so to kind of work on your part B.
After we draw it, do we write what kind of geometry or Vesper thing it has?
Yeah, right. Because in order for you to do part number 2, then you have to use your molecular geometry to explain why one is nonpolar and the other one is polar.
Mm.
Mm-hmm. So let's start with our Lewis structure for CF4. That's in this one. All right. So how many lone pairs does CF4 have? Or not lone pairs, how many valence electrons?
32.
32.
32, very good, right? 28 of those from fluorine, 4 from carbon. Carbon's in the middle. We have our fluorines going around it. Right, and then those should all be single bonds. Hang on. I'm going to turn off this video so that way I can flip. Difficult to write on the tablet. All right, so we got CF4 here, and then we have our sulfur, fluorine, or tetrafluoride.
34.
34, very good. And so what's different about CF4's Lewis structure from SF4? What should we also have on that SF4?
So, sulfur
Lone pair,
expanded on
the central atom.
Yeah, we need that lone pair on that central atom, right? Now, can sulfur have an expanded octet?
Yeah.
Yeah, right? And what atoms can have an expanded octet? How do we know?
I thought the rule was if it was past the third period.
Right? So sulfur is in the third period.
Yeah.
So is it past or is it starting with the third period?
Starting.
Starting, right? So as long as you're in the third period or below, you can have it, right? So
Okay.
phosphorus, sulfur, chlorine, those are kind of like the first ones that we see. All right, so we got our lone pair versus no lone pair. Now, when we're looking at this, what are the electron regions or groups? So how many electron groups does CF4 have?
4,
4, right? And SF4?
5.
5, right? And remember, we find this by looking at the number of atoms attached plus the number of lone pairs, and we're always looking at the central atom. We're not worried about the outer ones. We're looking at the central atom. So what's your electron geometry if you have 4 electrons, or if you have 4 electron groups?
Tetrahedral.
Tetrahedral. So it's taking on the basic shape of one of these fluorines up on top, one coming out on the side, one of these should be sticking up. No, sorry, sticking out of the page, and one of them should be going back into the page, right? And so you can kind of use that wedge to indicate something coming out of the page and that dash to show something going into the page. Okay.
Would it be okay if we drew these with, would it be okay if, like, when we drew these Lewis structures, we didn't like necessarily include that dash back and dash forward, but you could still tell, like,
so dashes should never be used with the Lewis structures,
or,
right? So when I ask
No,
for a
it's not.
Lewis structure, I don't want the dashes and stuff, right? I would want it to
Okay.
look just like this one that we drew up here, right? When we look at Vesper drawings, then that's when you get into those dashes, right? Now, I get that we're not all artists, so I don't ask you guys generally to draw the 3D shape of your molecules, but I would say that even though I can't draw that well, the dashes and the wedges are helpful in helping me visualize it. So I would strongly recommend that when you try to draw out your 3D structures, that you do use some of those dashes and those wedges, because at the very least, they help remind you that this isn't in the same plane. Okay. So for SF4, what should its electron geometry be?
Trigonal pyramidal?
Trigonal? No, it's not just pyramidal.
Bipyramidal.
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 Yeah, very good. And that's because we should have from that center, we have one going up, we have one going down, but we also have, we have one coming forward, one going back, and one flat in that plane, right? So we should have a top, a bottom, and then we should have that triangle at the equator. Now, where does our lone pair go? Do we put it at the equator or do we put it at the axis?
Equator.
Equator. And why is it going at the equator?
Oh, I just know it because it's a seesaw shape. So that works, but I don't know how to explain it.
All right. But you're right. It is at the equator. It is making the seesaw shape. Does anyone else remember why? Why do we add it at the equator?
It's to show that this is a polar. Well, I don't know if that's why, but it leads into this being a polar molecule.
So it leads into it being a polar molecule, but it's not at the equator just to make it a polar molecule.
Right.
So why did we choose the equator instead of the axial position?
That was the largest angle for the lone pair to bond pair, that we could have a repulsion that it wouldn't affect the geometry.
Yeah.
Or something
So
similar to that.
you're close, but what you said was like a little bit smoky, I guess would be what I would say. It means that you're close to the fire, but you're not quite it's not quite clear, right?
Yeah.
Can anyone help clarify that for Julio?
Is it we'll have less lone pair to bond pair interactions?
Right. And that is kind of where we're going, is that at the equator, because it's got this 120 degrees between these two, and it only has two 90s, it's going to have less lone pair bond pair repulsions. Right? So it kind of gives it the most space, kind of like what Julio was saying, but we're trying to minimize the repulsions because the lone pair, its repulsions are stronger. So if we can make those less by putting it at the equator instead of the axis, that's what we would prefer to do.
Yep.
All right. So we got it at the equator here. So as this is all set up, we said that this was seesaw in its shape, and this other one was tetrahedral for its molecular geometry because there's no lone pairs. So why is SF4 polar, whereas CF4 is non-polar?
Is it because it's balanced?
So it is because it's balanced, but how would you express that? Like, how would you explain that in a sentence, right? So actually it's probably gonna be a couple of sentences to justify it, but basically it's asking us in terms of molecular geometry, account for the fact that CF4 molecule is nonpolar, whereas the SF4 molecule is polar.
We bring in like dipole moment.
Yeah.
So dipole moment is good, right? Because polar means that you have a dipole moment. Nonpolar means you don't have a dipole moment.
Mm-hmm.
So that is something that's good to talk about, right? So that is a good justification, but you can't just say it has a dipole moment, right? It also is telling us that we want to use our molecular geometry, right? So it's giving you a little bit of a hint about how to talk about it. Symmetrical is sometimes a way to phrase that, but we do want to practice trying to write that out, okay? So take a minute and try to actually write out your explanation, because I feel like you guys have an idea about what is going on, but I just want you to put it into words, and then I'll tell you how I would grade a question like this. So I'll tell you what I'm looking for.
Can we see the question again?
Yep. Oh. So I'll give you guys a couple minutes. So at 1:34. All right, so I'm going to show my answer and then we're going to talk about what I would be looking for it. So for something like this, right? What I said was CF4 has a molecular geometry of tetrahedral, which results in all of the bond dipoles canceling out, giving no net dipole moment, making the molecule nonpolar. SF4 has a molecular geometry of seesaw, which results in uneven bond dipoles for the equatorial place fluorines, leading to a net dipole moment and making the molecule polar.
Nice.
Okay. So kind of what I'd be looking at for something like this is I'm looking for something like CF4, and I want to know that its molecular geometry is a tetrahedral. Okay, so that is part of it, because I'm looking to see whether you used your molecular geometry to help explain it. Okay. The second part of what I'm looking for is I'm looking for the bond dipoles to be canceled, right? So something about the dipole moments being canceled. And then that part coming out with nonpolar. Now, you don't have to use necessarily it just saying canceled. You could have said that they were balanced. You could have said that their positioning like counteracted each other, right? But something along that idea that the bond itself is polar, but because they are balanced, that there's no overall polarity. Second part, I would be looking for that seesaw name, right? So that you named your molecular geometry. And then I would be looking for this uneven bond dipoles. You didn't necessarily have to clarify about what was causing the uneven bond dipoles, but never hurts to explain it. And then I would be looking that you're saying that that means that it's polar. So you don't want to just say that because there is a lone pair, that means that it's polar, because that's not always the case, right? If we look at, oh, sorry. If we look at XE F2, right? XE F2 ends up with a Lewis structure that looks like this. Is XeF2 polar or non-polar? What do you guys think?
I think that's pretty polar. I mean, non-polar.
I don't know. Now you've covered both answers, so I don't know how you can be
I think it's
wrong.
polar.
But you definitely can't be right. So let's look at this, right? So what is its electron geometry?
Trigonal bipyramid?
Trigonal bipyramidal. So once again, we have our center here. We have our two axial positions, and then we have our equatorial positions here. So all of these lone pairs, where are they going? Are they going on the axis or are they going at the equator?
Both?
Equator.
The equator.
Oh, lone pair. Oh, my bad.
Lone pairs, yeah. And so our fluorines are here. Right? So we would see our electronegativity difference from that xenon to that fluorine. But as a molecule, is this polar or non-polar?
It's polar because the three lone pairs are in the same like plane, and they have the same well, not direction, but like force.
So does everyone agree with that?
No, I think it's non-polar.
All right.
Because,
and why do you think it's non-polar?
Because the three lone pairs on the, how do you say, equatorial position are, they cancel each other out with their dipole moments. They all cancel each other out. And then the two fluorines cancel each other out as well.
Yeah, right? Because if we look at it, like if we actually built this molecule, oh, sorry, that didn't. So if we add in our fluorines and our three lone pairs, you can see how our fluorine molecules are going to be 180 degrees away from each other, right? So one's pointing up, the other one's pointing down. And because all three lone pairs are on the equator, then it does set it up so that they can cancel each other out. And so this molecule is going to be non-polar, right? So XeF2 is non-polar. So just because you have lone pairs doesn't mean that it's polar. Now, I admit, often, if you have lone pairs, you are going to be polar, because often the other pieces are not going to end up being exactly 180 degrees, right? So if we only have one lone pair, we're going to be polar. If we had a tetrahedral with one lone pair, we're going to be polar. So often you do end up being polar, but it doesn't mean that it's a guarantee. Right? There's a couple of times where you can have a lot of lone pairs and still end up being non-polar. And so some of them are things like this, where you guys are octahedrals. Other ones are like square planars, where you guys can have lone pairs and still be non-polar. Okay. Do you guys have any questions on that?
Even.
Sorry, what was that?
Like the even number of pairs.
So
never. I'm trying to find. It's like I can't explain it, but I can see like a pattern, I guess.
So it's all based on your basic electron geometry, right? So XeF2 has 3 lone pairs. So it's not that it's an even number of lone pairs.
I mean, plus the, oh, okay, I see what you're saying, never mind.
Right, so it's just that when you have 5 electron groups, if you have 3 lone pairs, then your atoms will end up being placed exactly apart from each other. When you have 6 electron groups, then you could do something with 4 lone pairs, or you could do something with 2 lone pairs, right? And then that's when they're even, because the lone pairs are always trying to be on opposite sides, right? So it all depends on your electron geometry about how many groups you need or how many lone pairs you need in order to make them balanced. Any other questions on that part? So that's your beginning part, right? So that's where our Lewis structures kind of come into play, and our polarity, right? And our VSEPR geometries. Is there any other topics that you guys kind of want to go over?
Can you go over the lone pair, bond pair thing?
What about it?
Just like how to, because I know how to do the VSPR drawings, but I still get kind of confused on that part.
So there are 2 types of ways that you can have electrons, right? So our electrons are either going to exist as a lone pair, right, which is our unbonded electrons, or they're going to exist as a bonded pair, which is our bonding electrons, right? So the lone pairs are going to be the ones where they're only on one atom. Bonding pairs are going to be the ones where they're in the side of a bond, okay? Now, if this is your central atom, your lone pair, it's 2 electrons, and it only stays on that central atom. A bonding pair is 2 electrons, but they're spread between 2 atoms. They're basically connecting the 2 atoms that are forming that bond, because you have a positive side and a positive side for each. Right? So the idea is that a lone pair has more repulsive force because it's the same number of electrons as a bonding pair. So both of these are 2 electrons, so they're both kind of like a 2 negative charge. But a bonding pair is spread out over a longer distance because it's spread out between the nucleus of the central atom and the nucleus of the bonded atom. So it's got more space. So if you are the same charge, but you have more space, your charge density is lower. So this means that a bonding pair, right? So our bonding electrons don't have as much repulsive force as our lone pairs. So lone pairs have more repulsion than our bonding pairs because their charge is a greater charge density, right? They're the same amount of charge, but in a much smaller space. Does that part kind of make sense?
Yeah.
All right. So what we're trying to do as we're adding in lone pairs to our different electron geometries, is we would like to add them in where they get the fewest amount of interaction. The more interaction they get, then the more repulsion they're going to put onto that structure. So in the beginning, if we have our central atom and we put in one atom attached to it, it doesn't really matter whether we have lone pairs or not, because we can't ever change. It's always going to be a straight line between those two atoms. Same thing when we attach a second one. If we attach a second atom, that center is going to be over on the other side. But where we really start to see differences is when we have three atoms or three electron regions. And the reason for that is now we're going to have that triangle that starts to form. Okay. Now, is any of these positions different than the other position, or are they all basically the same? So 1, 2, and 3. Are those three positions the same, or is one different than the others? What do you guys think?
Or wait, what? Sorry.
So we're looking at a trigonal planar, right? So this is when we have just the triangle with the three geometries. And so we're looking at whether each of those outer atoms, if their positions are the same or if one of them is different than the others.
Oh, they're all equal.
They're all equal, right? And so does it matter where we place our lone pair?
Yeah.
So does it matter or does it not matter?
No.
No, it doesn't matter, right? So we can put them anywhere, right? Because wherever we put it, it's going to be as far away from the other ones as it can possibly be. So let's look at our tetrahedral.
No.
I think your sound's cutting in and out, Julio.
Wait, they're all equal. It does not matter where we put them up here.
Perfect. Thank you. Yep, you're right. So if we look at our tetrahedral on this one, are any of these positions different?
Yes.
Which one would be different?
The one on the equator.
So with our tetrahedral, all right? So right now, the way I drew it kind of looks like, if I can get this to work, kind of looks like this, right? So which one would you describe as being at the equator?
I guess none of them.
All right. And so the thing about a tetrahedral, right, is whatever one we have on top, if we wanted to, we could bring this one down, we could put this one on top, and they all look the same. Right? So wherever one is on top would be the same. And so they're all 109.5 degrees away from each other. Right? So just like trigonal planar, each of their positions are the same. So it doesn't actually matter whether we're at 1, 2, 3, or 4. All of those positions are the same. So that's why we don't worry about where we put the lone pairs for groupings of 3 or groupings of 4, because all of their positions are equal to each other. When we get to trigonal pyramidal, oh, not pyramidal, When we get into trigonal bipyramidal, now we have ones where their angles between them are not the same. Now is where we get equatorial and we get axial, right? And so we're going to talk about those. So when we have 5 things in there, let me try to arrange this so it looks like our drawing. So the ones that are opposite of each other, they're 180 degrees apart from each other. Do you guys see that?
You mean 90?
So the top one to the bottom one,
Opposite.
Mm-hmm.
Yeah. So the very
Yeah.
top one to the very bottom one, that's 180 degrees, right? Or it's 90 to the middle and 90 on down, right? But when we flip it, this one down here doesn't have something directly across from it. Instead, it has these two that are at 120 degrees from it. So not all of these positions are identical anymore. Instead, some of them have an opposite to them, and the other ones have 2 of them that are at 120. And so once we get to trigonal bipyramidal, now we have to decide where we're going to put those lone pairs, because it does matter, because they're not equal to each other. Does that part kind of make sense?
Yes.
Okay. And so how we choose where we're going to put it is we're trying to minimize the repulsions. Okay. And so if we wanted to look at them, we basically can look at, well, 90 degrees is kind of like our smallest angle. So we're going to make sure that our lone pair and bonding pair, we're going to have those in 90 degrees as little as possible. We would much rather have that lone pair and that bonding pair be at the 120 degrees. And so that's where we're looking at here. Well, if we put a lone pair up on top, it's 90 degrees away from this bonding pair, 90 degrees away from this bonding pair, and 90 degrees away from that bonding pair. So how many of those interactions does it have?
3.
3. But if we were to put the lone pair here instead, if I can ever rotate this over there. Oh, dang it. So if we put the lone pair here at the equator, how many bonding pairs would it be 90 degrees away from?
2.
2. And so that's how you choose whether you should put it at the equator or at the axial. Is you're looking at the strongest repulsion, and you're trying to minimize how many times you see it at 90 degrees, which is the smallest place. And so that's why our first lone pair goes at any of these 3 places at the equator. The second time where we add that lone pairing, we also end up adding it in at the equator. And that's because we're trying to keep the lone pairs apart from each other. Does that kind of answer your question about the lone pair bonding pair?
Yeah. It's just from the lab, when we had to like, the last one we just turned in with the, when it was like lone pair, bond pair, bond pair.
So you would have to look at all of those interactions for each of those models, right? And so they gave you models where one of them was like both of them at the equator, and then the other one, you had one at the axis, one at the equator. And then you had to figure out, well, how many of the different interactions there were. So you only counted the ones that are 90 degrees away from each other. Right? And so this one would have one lone pair to lone pair, because this lone pair is 90 degrees away from that one. Do you see that?
Yes.
And we would have our lone pair to bonding pair. We'd have 1 here. We'd have another one, 2. And we'd have a third one from the bottom to the side. And then our bonding pairs. That's going to be 1, 2. Does that kind of make sense?
Yeah.
Okay. And so that's what you're trying to do. I'm sorry, what was that?
This is chapter 9, right? I think I have to go over this again.
Yeah, so this is chapter 9. So what I would say is there's not as big of a focus on trying to determine all of these bond pair, lone pairs interactions, because once you understand how they're going to fill in, they're always going to fill in that same pattern, right? So there's a good reason why it goes to the equator instead of the axial, but it's not like you always have to recalculate these for every single structure that you do, because now that you know that they fill in at the equator, it will always fill in at the equator, right? So there's not like a whole bunch of these different setups.
Okay.
Okay. All right. So we want to talk a little bit about sigma and pi bonds, right? So let's go ahead and let's draw 2 atoms here, right? Now, does anyone have a definition of what a sigma bond means?
Yes.
All right. So what's a sigma bond?
Sigma bonds are single bonds. That's my best definition that I have.
So kind of, right? Single bonds are sigma bonds, but sigma bonds are not always sigma. Oh, sorry. Single bonds are sigma bonds, but sigma bonds don't only have to be single bonds.
Double bonds are sigma and pi bonds.
Mm-hmm.
And triple bonds are 1 sigma and 2 pi bonds.
All right. So you know what they do, but do we know about why? So when we talk about sigma, what is the difference between a sigma bond and a pi bond?
Sigma bond can rotate.
Sigma bonds can rotate. Oh, good. All right. So that is part of it. So sigma bonds, well, bonds happen because we have 1 electron ideally from 1 atom in its orbital, and it's sharing it with another atom and its orbital. So when we can get those orbitals to overlap, then they can form a bond, right? So a sigma bond happens when we get those 2 to overlap, and the majority of that orbital, that bonding orbital that we've created, exists in that direct plane between those 2 atoms, right? So they're kind of coming, let's see if we can do a visual. So you have your nucleus here and you have your nucleus over here, right? Your bond is formed because this one has an orbital coming out, and you're trying to align it with the orbital that from the other bond, so that way they can get this overlap, and that's where our 2 electrons are kind of circling, right? So sigma bonds happen when they happen between those 2 atoms, so kind of in this space in between, right? They can rotate because now they're kind of like top and top with each other. And so that's why sigma bonds or single bonds can rotate freely, right? We're always getting overlap between them. Does that kind of make sense? So you can imagine that your sigma bond exists, majority is inside that line between the 2 atoms. Now, when we have a double bond or a triple bond, we need to create another set of orbitals that are going to overlap. Now, could we just jam in more electrons into this space? Do you think that would work?
No.
No, right? We can't put any more electrons in there because electrons don't like each other, right? There's repulsion between them because they're both negative. So instead, we're going to take this overlap that's above and below our other atom. So let me try to make this a better drawing. All right, so let's look at something like this. So this one in red, that's our sigma bond because it exists right above and below. These blue ones are going to become our pi bond, right? And so what happens is you see how these kind of are pointing in the same direction? When they form that bond, then basically this area kind of starts to blend together. And we get something that looks like this. So our electrons are being shared between those two atoms, but they're being shared outside of that direct line between them. And so that's our pi bond. So the majority of the bond exists outside of the line between the atoms. Now, if you wanted to be close to our nuclei, so both of these black centers, would you rather be in the sigma bond or the pi bond?
Pi.
Sigma, I'm guessing?
The sigma, right? Because the red electrons right there in the middle, they're closer to both of those nuclei compared to the blue electrons. So we always form our sigma bond first because it's going to be preferred. Right? Those electrons are better, they're at a lower energy because they can see or be closer to both of those nuclei. Pi bonds form second because they are still good enough where we can see both nuclei, but it's not quite as good as a sigma. So we have our sigma bond in the middle, and then we have a pi bond top and bottom. Is that the only pi bond that we can make?
We also make like the sigma asterisk and the pi asterisk bonds.
So those are anti-bonding ones, and that's getting into molecular orbital theory. So yes and no, but we're not going to get into those quite yet. Instead, let's just looking at this one, we have one sigma and one pi. Are there any other pi bonds that we can form?
Could we pair the electrons?
So we are, this one that we already have drawn, that's already one orbital. So it's taken into both our positive and our negative. So those electrons are already paired. They can rotate between the top and the bottom.
What about the blue circle in the middle?
So the blue circle in the middle is just the gap. So it's like an empty space. It's not actually part of the blue. I'm going to pull up a picture of this and we'll see if this clarifies things for us. Yeah. So this section here, this top section is kind of where our blue one was on the other slide, right? So this, oh, that's not going to show up. So this section here, that was what used to be our blue. And this here is our sigma, right? So we've taken up the top of the atoms and we've taken up the center of the atoms. There's another place where we can fit another pi bond in, and that is going to be in this front and back of the atom. Right? So where this plane is, that green plane coming forward and back, is where we can fit another pi bond. So you kind of get something that looks like this, right? So you have a top one and a bottom one. You have that sigma bond right there in the middle, that's purple, but you can also fit a front one and a back one for that. Does that part make sense about sigma and pi? So about why we can fit two pi bonds, but why we can only fit one sigma bond.
So for the so is there 4 total pi bonds in this like diagram here?
No. So remember that for a p orbital has 2 lobes on it. Right? So when we make our pi bonds, the top lobe and the bottom lobe, that's all one orbital. So it's basically our p orbital is overlapping. I'm trying to get a picture of this. So this sigma bond is our s orbital is overlapping, and so there's only one for each. Our pi ones, it's a p orbital. So it's the top part of the p orbital and the bottom part overlapping with the top part and the bottom part inside of the next atom.
And this is for like an sp2 hybrid, or?
So the one on the left is an sp2 hybrid, and the one on the right is unhybridized.
Why is only the one on the left sp2 hybrid?
So we'll talk about that in just a second. Let's just, do we get how we have one sigma and 2 pi's?
Yeah, I think that part makes sense. So basically the top and the bottom, that's just one pi bond, basically.
That's just one pi bond. So each pi bond basically has 2 lobes, and each sigma bond is only one set in the middle.
Okay, yeah.
Okay.
Wait, were you looking at 2 different structures?
Yes. So,
okay.
So one of them had 2 pi bonds drawn. The other one, this one only has 1 pi bond drawn.
Okay. And is it always like this for like the double bond, and the other structure was the triple bond? It's always kind of like that layout?
I'm not sure what you mean by this layout.
So the pi and the sigma bond, that's is basically showing in that double bond in the Lewis structure, right? That's what.
So when we look at this, right, our sigma bond always forms first, right? So if you are a single bond, then you are just sigma, right? When you are a double bond, then you are going to be 1 sigma and 1 pi. And then a triple bond is 1 sigma bond and 2 pi bonds. So when we were looking at this structure, right, this is a double bond, and so that's why we have 1 sigma bond in the middle and then 1 pi. For this other one, this was a triple bond, And so it's got one sigma bond in the very middle right here. Then we had two pi bonds, one going top and bottom and one going front and back.
Yes, that's what I know.
Okay. Does that kind of clarify things?
Mhm.
Did you have a question, Chris?
I was wondering if like, according to like the lecture, it says I think it says that the pi bonds, they are between unhybridized parallel p orbitals. Does that mean they can only form in like the p orbitals that aren't hybridized? Meaning like there could be, since it's there can only be a maximum of 3 pairs in the p orbital, there can only be maximum of 3 pi bonds per molecule?
So in a second, we'll go over overlap. And so then we'll talk about what orbitals or what orbitals are coming together to form this, right? So we'll do that in just a second. Right now, what I first want to do is we'll finish talking about rotation, and then we'll talk about which orbitals kind of overlap with each other. And so we'll kind of touch on that the same as what Michael's question was.
Okay, thank you.
Okay. So when we're looking at this, right, I want you guys to try something. I want you to take your 2 pointer fingers, and I want you to put them together. Right? So your 2 pointer fingers coming together, that's like a sigma bond, right? And so you should be able to spin those around, right? And you don't have any problems, right? There's always that same overlap between your 2 fingers together. Right? Now, we're going to form our second bond. So I want you to take your middle fingers, and I want you to connect those now. Right? And now I want you to try to rotate, right? So now when you rotate, can you rotate as far, or do they start to get all twisted? Twisted, right? And so what's happening is that as you guys are going through and you're kind of, as you're making those extra bonds, then they get tied in to each other. And so our pi bonds right now, they basically form on that outer side of that sigma bond. And so their overlap prevents them from rotating. And so this is why once we make a double bond or a triple bond, our structures become locked in. Because when we start to rotate, when we have a double bond or a triple bond, those overlapped p orbitals, they get all twisted and they would have to break in order for us to flip all the way over. And so that's the difference between why when we form a double bond or a triple bond, we no longer can rotate between them. Okay?
Could I ask a quick question?
Mm-hmm.
So why do we like observe it like when we rotate around the sigma bond, rather like, because if we could also rotate just the whole molecule, right? Like, and then everything will be able to rotate.
So this happens more when you guys have different things going on one side compared to the other, right? So when you have a molecule that looks like this, right now, we could say, well, here, let's do this. Right now, our oxygens look like they're on opposite sides, right? But because it's a single bond, we could have also drawn it to look like this. We could have had it rotated over, and that would be the same. That molecule is still the same, even though now the oxygens are both on the same side. Okay?
I see. Okay.
But that's different than if we had a double bond. If we have a double bond here, now you can't spin on that far side. And so you would have 2 distinct molecules. One of them where you have the oxygens on the same, and you would have another one where your oxygens were across from you. And this actually becomes a big problem, or maybe not a problem, but it opens up new chemistries, especially in like the biological field, right? Where it's not just about what's inside your molecule, but also their shapes, right? And so this is something that you see when we talk about like enzymes for proteins, right? Not only does your protein have to have an opening for that enzyme, but that enzyme has to perfectly fit in there with that shape. And so now these 2 shapes are very different than each other. So your ability to rotate or not rotate does matter. And it's just because sometimes while we can spin the whole molecule, not the whole molecule doesn't always align with each other once they start to get locked into place.
I see. So if we have that double bond distinguishing the two molecules, then would it mean like one of them would have like more dipole than the other if it's not evenly distributed?
So like one of them, right? Both of your dipoles are heading in this direction. The other one's headed down and one's headed up, right? So you would have distinct dipole moments for each of these molecules.
For sure.
Mm-hmm. All right, so now that we have the understanding of a pi bond and the double bond and the sigma bond, let's talk about how they form, right? So when we have oxygen's orbital diagram for its valence looks something like this. We have 2 electrons in its 2s, and then we have 4 electrons in its 2p. So if we were to think about that oxygen atom, or that nucleus of it, it has these 2 openings to form bonds, and those would be in its p orbitals. Right? Does anyone remember what shape our p orbitals are?
It's like an 8.
Looks like a dumbbell or an 8. Very good. So we have one that comes up and bottom. We have one that goes side to side. So kind of like on, our Y is the one in the green, our X is the one in the blue. And then we have our front and back one, which would be the one on our Z. And we'll pretend like the Z one is filled in right now. That's going to be this filled in orbital. Okay. So when we form a bond with that oxygen, right? Let's say that we're putting another oxygen over on this other side. They want to share those half-filled orbitals. And so we're going to try to get oxygens, the second oxygen, its orbitals to line up with the first oxygen openings. So you're basically trying to find these half-filled orbitals and you're trying to get them to mesh together so that they can overlap. So second oxygen, we can get its blue orbital to overlap, and then the other one sticks out on that side. And its green one is going to stick up top and down at the bottom. So one of those electrons comes from the first oxygen, and the other one comes from the second oxygen's orbital. And so do you guys see how that bond formed between them?
Is this just one oxygen atom, or is this?
So this is 2 oxygen atoms. We have one over here on the left, and then we have another one over here on the right. So does it make sense how we formed that first bond? No? So if you kind of wanted to imagine it, our first oxygen kind of looked like this, and then our second oxygen kind of came over, overlapped its p orbital, brought its electron with them. So that's our first bond that forms. So is this a sigma bond or is this a pi bond?
Sigma.
Sorry, what was that?
Sigma.
Sigma. So this is our sigma bond. And so you could say that that sigma bond is formed by oxygen's 2p orbital overlapping with the other oxygen's 2p orbital. Right? That's what's actually forming this bond. And so that's when you go back to the slides, when it's talking about these overlaps, they're talking about what elements bond is overlapping, or what elements orbital is overlapping with the other ones to form that bond. Okay, so that's our sigma. Our pi bond is going to be this electron up here, along with this electron from their p orbitals. They're going to start to blend together, top and bottom. Okay. So now all of this becomes a bond, and that's going to become our pi bond. So our pi bond is now also between the oxygen's 2p orbital and the other oxygen's 2p orbital. Okay. And so this molecule would look like this in its Lewis structure because it's a double bond between that oxygen and that oxygen.
Amá, ¿tienes una tarjeta del PG&E?
I'm going to mute you for a second, Rosa. All right. Do you guys have any questions on that part?
So I kind of get how like that orbital goes, and then the sigma one and then the pi one on the top and bottom.
Mm-hmm.
What about the one kind of on the left? Is that just empty?
So the one on the left is just empty for now, because actually it's a filled orbital, right? Because its partner is this one that's being shared in the middle. So now this side is also filled. Right?
Oh, is that is that where the lone pair goes?
So that's not where the lone pair goes. The lone pair is existing in the third p orbital. So this block here, this filled one, that one's coming front and back. And so we didn't even bother drawing them in because it's already a filled orbital.
I don't understand that.
Right? So if this is oxygen, if this is an oxygen atom, before it's even filled, its 2s orbital is already filled, right? So from there, we have a p orbital that goes top and bottom. We have a p orbital that goes side to side. And we also have a p orbital that's coming kind of straight forward and straight back. So if you wanted to imagine this as being a graph, we'd have an x, we'd have a y, and we'd have a z, right, for our p orbitals. So right now, if this is our atom in the center, it's got p orbitals coming from one side to the other, and that's this one here. It's got p orbitals coming up and down, and that's that one here. And then it has a set coming front and back, which would be these red ones over here. Does it make sense now where all of our little circles are coming from?
Yes. Yes.
Yeah. So where's like the 2s orbital in all of this?
So the 2s orbital in all of this would be right, like kind of in the middle of this as a giant sphere. So it overlaps with your p orbitals because it's just taking up that whole center part. And so that.
So kind of in the drawing that we just did, like we don't really have to worry about the s orbital in this case. We can just those bonds here are just the p orbitals. And
so basically when we start to draw these kind of things out, we ignore all of the filled orbitals, because if they're filled, then they already have their shape and then we're not worried about them, right? So the only ones that I drew were the unfilled ones. I'm trying to see if I have our slide that has.
It be in that middle circle though, right? I mean, I know that's the atom, but like, because it's a spear shape. So
this is what it looks like when you have all your S, your P's, your D's, and your F's, all of them put together, right? So this is kind of why we get that idea of a nucleus as being like this circle, right? Or an atom as being as this circle, right? So once we overlap them all, it looks like this. But as we're going through it, then we can break it down into the different shapes. So we have our F's, our D's, our P's, and our S. So the S kind of takes on that entire sphere. And then our P takes on the ones coming up, the ones going side, front and back, and the ones going side and side. So when we're looking at our orbital here, one of these sets of p orbitals is filled, right? And so because it's filled, then it's not going to be engaged in the bonding process. It basically is a lone pair. And so we're just going to go ahead and we're going to take that out because it's not going to be involved in the bonding process.
And
Does
then
that
the
kind of
two,
make sense?
Yeah, so then the 2s one would also be like the other lone pair, right? Because oxygen has 2 lone pairs.
Yes, so the 2s one is the other lone pair, and so that one would be like a giant circle encompassing all of this, and we're not going to draw that because it's not going to get involved in this process.
Okay, so basically the ones that form bonds, it's kind of like when you just have it half filled, like your orbital has 1 electron in it by itself, so then like when it connects to the other one, it gets that filled.
It gets that filled, right?
And then
So
if
we were to look at-
if it's completely empty, like it has no electrons in it, then it's just an empty orbital.
So if it has no electrons in it, then it's just an empty orbital. So it still has that space that it can move into, but it would just be empty.
Okay, yeah, that makes sense now.
So now that we have this one, right? So that's where our oxygen kind of took on its setup, is we didn't bother drawing in the one that was already filled. Okay. Now, this gets more complicated, right? So let's look at a molecule like this. Okay. So we're going to just talk about the carbon for a second. So that carbon, how many electron groups does that carbon have? Actually, I'm going to zoom in on this so we can make it bigger. So that carbon, how many electron groups does it have? 3. And so what would its hybridization be? sp2. And so what this is telling us is that that carbon, normally its orbital diagram looks like this, right? With this being our S and this being our P. However, because it's trying to connect with all of these different things, what it's doing is it needs to hybridize its S orbital with 2 of its P's, so it makes a new block of orbitals. So these are the hybridized orbitals, sp2, and then it keeps 1 orbital left over, which is its P. And so those electrons that it had, it kind of splits those out between all of their orbitals. And so this is the 4 openings that this carbon has. So this is where hybridization comes into play. So when we're saying that it's an sp2, it's because it really does have to mix those other orbitals. And that's because we want that carbon to look like it has an orbital going up, 1 going to the side, and 1 going to its side this way. So that way it can take on that trigonal planar shape. Right? So if it doesn't hybridize, then the S, the P's, they don't look like a triangle. And so that's where we have to get this mixing to occur. So that's where that hybridization comes from. Does anyone have any questions on that part?
I kind of have a stupid question about the oxygens. So like back in the other chapters, so the electron configuration, it 2s 2p4, right?
Yeah.
Okay, so but for the hybridization, it's sp3.
So hybridization, the difference between them is that hybridization is only the orbitals, right? Whereas electron configurations, those are the number of electrons, right? So you get S2 and P6 because that's how many electrons are in there. Your hybridization, you get sp3 because there's only 1 s orbital and there's 3 p orbitals.
Okay, thank you.
Now, all carbons don't have the same hybridization. It only depends on their bond, like what they're connected with, right? So in this specific molecule, carbon has an sp2. In other molecules, carbon could have no hybridization, or it could be sp3, or it could be sp, right? So hybridization is molecule specific. It's not it's not elemental, right? So not all elements have the same hybridization. So for these hydrogens, do they need to hybridize?
No.
No, they don't. Very good, right? And so pretty much only if you're connected to more than one atom do you have to hybridize. If you're not connected to more than one atom, then you don't have to hybridize. So the H doesn't need to hybridize. And the oxygen doesn't need to hybridize. So it's only that central atom in this case, because they have to create that specific shape of the molecule that we're looking for, right? So carbon is going to have this interaction between its sp2s, right? So it's got 3 sp2s that are going to be involved in that. So when we start to draw this, we kind of have our carbon molecule here. It's going to connect going into triangle and the triangle this way. And so these are their 1 electron for each of them inside of their sp2. And it's got a third one coming this way. And it's got 1 electron there as well. So what I'm going to do is I'm going to start to overlap the other atoms onto this. So for our hydrogen, its orbital diagram looks like this. So when it overlaps with this carbon and it brings its electron on, what orbital is it overlapping?
The P?
So look at hydrogen's orbital diagram right over here. Where is its opening?
I don't know what you mean by opening.
Right? So this box that we have, right, is its 1s. How many electrons can we fit into a box?
2.
2, right? How many does it have in there right now?
1.
1. So hydrogen has an opening to take in 1 more electron inside of its s orbital for it to become a full complete orbital, right? So if we took in another one, then it would now be a full orbital and it would be complete, right?
So would that become a sigma bond?
So this one, the first one between them, that was always going to be a sigma bond, but you're right, it is a sigma bond. And it's forming from the overlap of hydrogen's s orbital and carbon's sp2 orbital.
And why do we have to include the S? Because isn't that, could you just say P2 orbital? Well,
No, because you have to say that it is hybridized, right? So that hybridization is because of a mix of the s orbital and the p orbitals,
okay.
right? If you just said the p2 orbital, that would mean that it was unhybridized and it was just its p orbitals. So this hydrogen down here, is it going to do the same thing as that type hydrogen, or is it going to do something different?
It should also form the hybridized bond.
Should also do the same thing. So it's still going to form a sigma bond. And that's going to be between its s orbital and carbon's sp2 orbital. All right. Now, over here, we're going to have our oxygen. And oxygen had that orbital diagram of this, right? So how many bonds did our oxygen need to form with this carbon?
2.
2. So we're going to form the first one first. So something from that oxygen is going to overlap with that sp2 of that carbon. And so is that going to form the sigma bond or the pi bond?
It'll be our
Sigma.
third.
Very good.
Sigma.
It's going to be our sigma bond. And so that's going to form between oxygens. And what opening do we have for that oxygen?
Two P.
Right? There's 2p. Right? And that's overlapping with carbons. What kind of orbital?
SP2.
Very good, sp2. So our sigma bonds pretty much always, well, if we have hybridization that's occurring, then that sigma bond is going to be the overlap of those hybridized orbitals. Right? The double bonds and the triple bonds, those always form with the unhybridized orbitals. So we're going to talk about that in just a second here, right? And so that's how we can determine what orbitals are interacting for it. So like, let's look at this one for our double bond. So for our carbon, right, we've done our 3 sp2s, right? We had one going to this hydrogen up here. We had one going to the hydrogen at the bottom, and we used up a third one going to that oxygen. So what other orbital do we have available to take part in this double bond that we need to form with that oxygen?
It should be the pi bond and oh, sorry. Go ahead.
Oh no, go ahead. I was asking a question. Go ahead.
Oh, I think it should be the pi bond because the p orbital is the last one that needs to be filled.
Right? So the p orbital is the last one that needs to be filled. So you can kind of imagine that this one has filled with an electron from the hydrogen. This one has filled with the other electron from the other hydrogen. And this one has filled with the electron from that oxygen, right? So 1, 2, and 3. So our double bond is going to form from this unhybridized p orbital. Running out of colors, running out of space, right? So that's kind of the up and down orbitals. Oxygen has its own unhybridized p orbital left over still. And so that's going to form that top and bottom one. So in the same way that we kind of form this one coming to the top and coming to the bottom, that's where we have those unhybridized p orbitals. So that gap that we still have here on this one, that's going to form for that second bond. So that's our p orbital, or sorry, that is our pi bond. And it's forming between oxygen's p orbital, which is kind of like this second one over here, because we've already filled in that one, and carbons, and this would be its unhybridized p orbital because it's this box right there. And so that's how you can find all of your interactions between all of them.
I have a question. So the hydrogen, how come we included the for the sigma bond? We included the sp2 for the carbon. We included the s orbital, but in the pi bond, we only did the p.
So when we were looking at this, right, what shape, what kind of electron geometry do you have if you're sp2? How many electron groups do you need if you're going to be sp2 hybridization?
Is it 3?
3, right? And so what kind of electron geometry do you have if you're 3?
Trigonal planar.
Trigonal planar, very good. So our carbon kind of looked like a triangle, right? And so on one of them, we put a hydrogen. On the other one, we put a hydrogen. And on this third one, we put an oxygen. Okay. Now, those 3 orbitals kind of go in those directions. And so each of these would be considered an sp2 orbital, right? And so there's 3 of them, right? So we have 1, 2, and 3. So for our first ones, those were the ones that were drawn in the blue. And so whenever they interacted with something, then we always included the sp2 because that was that type of orbital that was interacting with the other atoms. So that was kind of before we put it all on in this green stuff. So let's take that out. All right. So this was when we did only our sigma bonds. So that's why we include sp2, is that those first 3 bonds that we formed, they all had that sp2 orbital from that carbon causing that overlap, so that way we could get its shape. Does that part make sense?
Yes, I get it now.
Okay. And so what bond do we still have left over that we haven't drawn in yet?
P.
We still have that second bond for that double bond. And so that's why on the pi bond, it's only the P, is because it's no longer one of these 3. It's instead that top and bottom bond that forms that pi bond for that second, for the double bond.
Thank you.
And so a double bond and a triple bond always forms from the unhybridized orbitals. And so it's always those unhybridized p orbitals. And that's because if you were going to have a double bond or a triple bond, you are always going to have electron groups less than 4. Right? So you're going to be something like this, where we had an electron group of 3, or you're going to be a triple bond, and you're only going to have an electron group of 2, right? And so it's always giving you these extra p bonds, or sorry, extra p orbitals that can overlap with that other molecule or that other atom without hybridizing. And so that's why your double bonds and your triple bonds are always formed by unhybridized p orbitals.
So really, like one carbon, like it can, so a carbon can have a hybrid, like hybrid orbitals, but it doesn't necessarily just have like the hybrid orbitals. So when, like in this example, it made the sp2, but then there was still that 1 p left over.
Exactly, right? So carbon doesn't only have hybridized orbitals, or doesn't only have unhybridized orbitals. It can have a mixture of them.
So it then, like, what if I wanted to say, like, okay, just like what are the orbitals that it has, like normal, right? Like sp3, which is what we normally call it. Like, what would that be referring to again?
So you aren't going to be able to say what would it normally have, because it's all molecule specific, right? So if you have carbon attached to 4 different things, which is what we see often, then it's sp3, and all of its 4 orbitals have been split apart, so it has that tetrahedral shape, right?
Yeah.
But it could also be like this, where it's sp for its hybridization, and so it has 2 sp orbitals and 2 p orbitals, making those bonds.
Okay, I think I actually asked like the wrong thing. I meant to say, like, when we were doing like and we just knew it as like say like s2p
Okay, so
s2p2, like what would that be?
So we would have always called it as those are the electron configurations.
Okay.
But it's not. Basically, hybridization comes about as we try to better explain why do molecules look the way that they do, right? Because before hybridization, it wouldn't make any sense for 3 groupings, right? So like if you had 3 atoms attached, that it would look like a triangle planar, because none of our orbitals look or point off in the 120 degrees, right? And so we weren't able to get them to overlap. We're using p orbitals and s orbitals and d orbitals to look like how we saw the molecules. So then they said, well, what if there's a mixing of molecules that occur, or a mixing of orbitals that occur? And that's why they take on these funky shapes. So that's how they explain hybridization. Molecular orbital theory is like that next step up.
Sorry, go ahead.
No.
So hybridization is kind of like it's like modifying the electron configurations to like support molecules.
Exactly. So it's basically modifying your orbitals so that they look more like how we actually get them to look. Right? Like how experimentally we found out that they look like this. And so we had to adjust our theory to now match what we would see.
So for the exam, like, how is this going to be presented on the exam?
So if you had something that looked like this, maybe what they would do is that they would draw something. No, let me get this one back up. Maybe they would give you something like this, and they wouldn't have any of the like the sigma, the CSP to CSP, and basically you would be filling in this section for each of them, right? So they might draw that out, and they would say, well, this is bond 1, this is bond 2, right? This one could be bond 3. What type of bond is it, right? And so you would have to tell me that bond 1 is sigma, right? Bond 2 is pi or whatever it was, right? And then it could ask you what the interactions are. And so if it's asking you for the bond interactions, then this is where you're looking at trying to fill in that CSP, or whatever that part is.
Okay.
So that would be farther along than just like your beginning ones. So your beginning ones style questions would be, what's your Lewis structure for this? Once you have your Lewis structure, what's the number of electron regions, electron geometry, molecular geometry, is it polar, is it non-polar, right? And then intermolecular forces that would be there, right? And so that would be like your more basic question. And so this would be that next one where it's asking you, what's the difference between a sigma bond and a pi bond? What kind of bond would this one be? What's the orbital overlap that's happening here, right? So that would be like a more involved or more advanced problem for that topic.
Okay, thanks.
Mm-hmm. Any other questions?
Is it or do we usually prefer to hybridize orbitals over expanded octet, or
So you can only have an expanded octet if you hybridize orbitals, right? So I think what's throwing you off is, so valence bond theory is kind of what the beginning of this one is all talking about. And so hybridization happens all the time, right? And basically it's happening because we are trying to get our molecular structure to really look like what we started to see, right? So it's not that we would prefer one over the other, they kind of go hand in hand, right? So you're still creating your Lewis structures based on the same set of rules that you always created them, right? Because a Lewis structure does do a good job in telling us how things are connected. And so we would form that expanded octet if you are in period 3 or greater, and it would reduce your formal charge, right? Once you have your Lewis structure up, then you guys find your number of electron groups or regions attached, and that will tell us what your hybridization has to be in order to accommodate it, right? So your next part from your electron groups or regions gets you to what hybridization has to occur, right? So your hybridization doesn't change right? So your electron group number tells us what the hybridization is. Those things will always match.
Oh, I'm sorry. I think I meant to ask, like, in the context where, like, would we rather prefer double, triple bonds rather than, like.
So that's a great question. How could you guys decide whether you should have a double bond or a triple bond versus an expanded octet? What should you be using to evaluate your Lewis structure?
Formal charges.
Formal charges, right? So look at your formal charges and kind of go with that. And so basically for our class, primarily what we're looking for is our formal charges and using that to come up with our best Lewis structures, right? And so if we're looking at our formal charge, what's the best formal charges to have?
0.
None, right? So we would like to have the fewest number of formal charges. So if we can get 0, that would be best. If we can only get 1, then that'd be 1. Now, is a +1 better or worse than the +2?
Better.
Right? So we would like to have the lowest formal charge. So 2 + 1s is better than 1 + 2. Right? So we would rather get to the lowest number. And then from there, we would rather have no formal charges, which would be better than 1. And then the last part is we would like our most negative formal charge on the most negative or most electronegative atom.
What do you mean by that?
So if you had the choice between fluorine and chlorine getting a formal charge, who should get it?
Fluorine?
Fluorine, right? So we would like our fluorine to be the -1 more than our chlorine, right? In the same way that if you had a carbon and a fluorine, we would much rather have the fluorine with the -1 than the carbon with the -1. Now, on that note, what ways, like what exceptions to the octet rule are there?
Period 3 and below can have expanded octet.
Right, so we can have an expanded octet. Very good. What others?
Incomplete octet?
We can have an incomplete. And so what causes an incomplete? Or what kind of atom or elements are involved in incompletes?
It was like specific ones, right?
Right.
I know
So there are
hydrogen
specific ones.
I was gonna say, I know hydrogen doesn't need 8 valence electrons, but I can't think of any of them.
Right. So hydrogen and helium, they don't need 8, though generally we don't talk about them as much when we talk about incomplete octets because they're following a duet rule, right? And so that's where they're a little bit different. Right? Does anyone have any thoughts about where we might see an incomplete or a really common element that does incompletes?
Could it be like
I think it was Be, beryllium, and then boron, and then the aluminum were like the main ones.
Right? Those are the main ones. Very good, right? And it's because they are low in their period. And so beryllium really is almost like it's giving away its electrons to become helium, boron as well, aluminum as well, right? So they're more a little bit on that ionic side, but because they have such high electronegativity, or not high, but higher electronegativities, they still can be involved in covalent bonds. They're just very polar covalent bonds, right? And so those are like our normal 3. Right? Is there any other exception to the octet rule?
Odd number octet?
Odd number. Very good. And so let's try something like that. So let's look at PO3, phosphorus trioxide, right? What Lewis structure would you guys come up with for phosphorus trioxide?
It has 23 valence electrons.
Very good. 23 valence electrons. So you might end up with something that looks like this, right? But if we look at our formal charges, this one is going to be a -1 here. This is a +1. Right? So what would be a better Lewis structure?
Is that a lone pair on the?
So it's not a lone pair, it's just a lone electron.
Would it be to make a triple bond
Between what?
on the one of the phosphorus and the?
Right? So if we make a triple bond, what that is going to do is that is going to increase this formal charge and decrease that of oxygen. So how else could we improve upon this?
Oh, sorry. Can phosphorus have an oxidation number of 6?
What do you mean an oxidation number of 6?
Well, if there's 3 oxygens and each of them is 2- and there's no charge, that means that phosphorus has to have +6, or?
So that is something different. That's like not even that's not involved in this because this one, our oxygens are not -2.
Oh, I thought, so is it because oxygen is, I remember like we said oxygen is always -2 unless it's ozone or something else. So would this be another?
So this could fall into that exception rule
Okay.
for the oxygen because basically one of them in there is acting a little bit like a peroxide.
Okay. Okay, thank you.
But we're looking at the Lewis structure. So how could we improve on this Lewis structure?
I think oxygen would be more electronegative than phosphorus. So if you tried to swap the formal charges, essentially.
And so how would we do that?
Let's see. Well, you could make one of the like with the oxygen that has the plus formal charge right now. You could like remove one of those double bonds on like the phosphorus, and
Yep.
then convert that to lone pair on the oxygen.
Good. So that gives that a minus and this a plus. Or no, now that's a 1, 2, 3, 4. Yeah. So now that was a minus and 2, 4, 6, 8.
But then I guess the formal charges don't align with the molecule charge, so you'd have to.
You're right. Now we're okay, right? Because phosphorus has 5 minus 1/2 of 10. So that's 0, right? And our oxygen over here on this side is going to be 6 minus 1/2 of 2 minus 5. And so that's also going to be 0. So that's good.
Oh, this works out?
This does work out.
So that oxygen on the left just has an incomplete octet.
So the one on the left does have an incomplete octet, and the phosphorus in the middle has a expanded octet.
Ah, okay. And that's still better than having formal charge.
So that's better than having formal charge. Now, did anyone come up with a different Lewis structure?
These take like a long time for me. How would we, is it just something you have to kind of practice on? Because I don't really.
So Lewis structures are something that practice does make them faster, right? Because so when you see it, there's things that you know, right? So phosphorus forms like 5 bonds or forms like 3 bonds in a lone pair. There's like familiar patterns that they start to fall into, but they don't always follow those patterns, right? So I don't just teach you guys a bunch of patterns. It's more like an iteration type of process.
Oh no, I'm at the formal charge part, not the Lewis structure.
Yeah, so formal charges, it's just a practice thing, because the more that you do them, then the sooner you can do them in your head and you don't have to write them all out, right? So if I look at this oxygen, I can see, well, oxygen is 6. It's got 2 coming from its bonds, and it has 4 coming from its lone pairs. And so it's 0. So it's just like, I can just count and I can see if we're up to 6, right? So for this phosphorus in the middle, we have 1 from its lone pair, 2, 3, 4, 5, 6, 7. And so this one's a -2 for its charge. And then I actually think I have too many electrons in here. So that one also doesn't work. So that's the fastest way to do them, but it's not easy, I guess. So our best Lewis structure was going to be this one here. Now, hypothetically, if we were looking at this one over on our right, what would you guys say our electron group number is? Just before we finish on up.
4.
Right? And so that's because it's got 3 atoms attached, and then we have the 1 lone pair. So even though it's not a complete lone pair, we would still count it because it's still going to take up a space, right? And then when we get an extra electron, then that would fit in there. And so that's where the next one would come, right? But you're right. We should have it as if its electron group is 4. Excuse me. And it would be tetrahedral in its shape. So whenever you guys deal with odd numbered electrons, even if you only have 1 electron by itself, treat it like it's a lone pair for its shape, molecular geometry, everything like that, because it still needs to hold that space, right? We still have to make a space for that lone pair, and it's going to look more like it has a lone pair than it behaving like there's nothing there. Does that kind of make sense?
Yes.
Wait, so you just said if there isn't a lone pair, still act like it kind of does? Bless you, by the way.
Thank you. If there's only 1 lone electron, treat it like it's a lone pair, right? So right now with this phosphorus, it's just got 1 lone electron up there at the top, right? But we're going to give it space like it's a lone pair. So that way its shape, instead of being trigonal planar, like if we treated it like it had no extra electrons, it's going to be more similar to a tetrahedral than trigonal planar. So even though it's only 1 electron, so it's not a complete lone pair, it's only half of a lone pair, it's still going to behave more like it was a complete lone pair than like it was no lone pair.
When you did the formal charge for oxygen right there, you did 6 - 2 - 4, which makes sense. But I remember you gave us, so it was valence electrons minus number of unbonded electrons minus 1/2 of bond electrons. So can we
Yes.
just do it that way then? Because that's easier for me to remember.
Yeah, so you can do it that way.
But the way you did it on the.
So that part, it doesn't, either one works, right? I think I tried to do the unbonding electrons and bonding electrons because at that time you guys are getting a lot of new language. And so I'm just trying to keep it uniform. And so we're always dealing with them as either all individuals or sets, right? Because what I've seen is when I teach you guys as doing the number of bonds minus your number of unbonded electrons, people start to mix that up with your lone pairs. And so it becomes like a little bit of a disaster. So either one is fine. As long as you're getting to the right value, then that's okay.
I just wanted to add, like, it kind of helped me to think of like for calculating formal charge, we're still considering like each individual electron, right? But when we say like the bond, we divide it by 2 because there's 2 in the bond, right?
Exactly, right? So for this one, we're treating it like each of them gets one of those electrons. So we need to split them in half because each of those atoms involved is taking half of it.
I kind of just count every line as one.
Yeah, because the 1/2 thing was kind of messing me up, to be honest.
And that's fine. So you can count every line as one. That's something you just, there's like, it makes sense. And once you're familiar with it is a good thing to be able to do. The part that I worry about is when you first learn it that way, there's a conceptual part that can sometimes get lost where people start to forget that that bond is actually 2 electrons in there, right? Things along that line. So if you feel comfortable that you know that that bond is 2 electrons, but when you get to formal charges, you just want to count it as 1 because half of 2 is 1, that's okay.
Okay, cool.
Yeah. So it's kind of like one of those shortcut things where it's not wrong. It's not going to get you wrong. Sometimes I just think conceptually it can trip you up in the very beginning, which is why I don't teach the shortcut.
I understand.
Mm-hmm. But perfect. So that kind of brings us to an end for this one. So we'll do intermolecular forces tomorrow.